Part 6 for three-phase transformer connections is actually objective 4, which is the delta to the delta 4-wire connection. It is not a common three-phase transformer connection. It is used sometimes in certain locations, not an awful lot. It is sort of a unique connection. What is unique about this connection is that the secondary has a tap in the center of the B to C transformer, which allows three-phase loads and single-phase loads to be fed from the secondary. Ordinarily, delta secondaries can only feed three-phase loads. When we look at how this is connected, on the primary we have a regular delta where the lines A, B, and C are connected to H1 of the single-phase windings, and the end of each winding is connected to the beginning of the next winding. End to beginning, end of B winding to beginning of C winding, end of C winding to beginning of A winding. On the secondary, we do the same thing. The lines A, B, and C come off of X1 on the secondary windings of these transformers, and the end of each winding connects to the beginning of the second winding. End of A phase connects to the beginning of B phase, end of B phase connects to the beginning of C phase, end of C phase is connected back to the beginning of A phase. Then, on the B to C phase, a tap is made at the midpoint of that winding, which gives us a common conductor for our single-phase system. And our single-phase system consists of line B, line C, and this common conductor. And this creates a single-phase 3-wire supply that can be used for single-phase loads, with the common wire acting as the neutral. And in delta 4-wire systems, the phase A conductor is always the one with the highest voltage to ground. Code requires us to have the tap made in the B to C phase, and that the high leg is always going to be the phase A conductor. And most of the voltages that we have with a delta 4-wire system are pretty straightforward to calculate. So I will just go through the voltages and give you the answers. On the primary, it's really straightforward. Now, if the primary line voltage is 2400 and the primary phase voltage is 2400 because it's a delta connection, the secondary phase voltage will use the ratio. That ratio always takes place from phase primary to phase secondary. So if the primary phase voltage is 2400 and the ratio is 10 to 1, the secondary phase voltage will be 2400 divided by 10, or 240 volts. The secondary line voltage, of course, because it's a delta connected secondary, will be 240 volts as well. Now again, we have on the secondary a single phase supply between B, C, and the center tap we have here. So if this is 240 volts, phase B to C voltage, and we have a tap right in the center, the voltage from B to that point will be half that voltage, 120 volts. And the voltage from C to that center tap will be 120 volts as well. The one voltage that's left that we can see on the secondary is a voltage from A to that center point. This is called our high leg voltage and can be a little difficult to calculate. The next slide will give us a hand understanding how that would work. There are a couple of methods of determining the high leg voltage. One method that can be used to solve the high leg voltage is to make a triangle of the voltages that we have on each phase. 240 on phase A to C, 240 on phase A to B, 240 on phase B to C with a center tap. And once we have that center tap, it does make a triangle for us as well, where the hypotenuse is 240 volts and the horizontal side is 120 volts. And if we're looking for the vertical side, that vertical side is the square root of the 240 volts squared minus 120 volts squared. So you can go through it this way to figure out what that high leg voltage is, or there's a much easier way that we often use. We just simply say that the A to N, the high leg voltage, will be half of my phase voltage. So if my phase voltage is 240 volts, it will be half of that, or 120 volts times root 3. And 120 volts times root 3 will give me a high leg voltage from A to the center tap or neutral point of 207.8 volts. To memorize a little formula like this is, I think, an easier way to do it than to try and figure out the vector math for it. And that's really all you need to know for delta to delta 4 wire three-phase transformers. The only other thing to keep in mind is that code is very clear about the fact that on the secondary of this transformer, when we feed panels with this secondary, the only thing that we can have in a single phase panel is line B, line C, and this center tap neutral. We cannot have line A in a single phase panel because that will not give us 120 volts. It will give us a higher voltage, 208 volts, and so we cannot have line A in a single phase panel. And in any three-phase panel that we have, the only lines that can be in it are line A, line B, line C. We cannot have this neutral in our three-phase panel because it is not a three-phase neutral. It is just a center tap on this single phase and works as a single phase neutral, but that is it. That's it for now.